Okay, this is question number 4 from the section 6.2 online homework. We're trying to find the area between two curves. It's a pretty simple case for setting up the integral because if we use a vertical slice, so we have a point, a value x where we're going to draw a slice, then the top coordinates of that slice are just x comma this equation of the top curve, and the bottom slice is x comma 1. The bottom of the slice is always when the y coordinate is equal to 1. So the difference between these two y coordinates is going to be the height of that slice, and the width is dx, or delta x for the first part of it. So our rectangle area will just be the difference in these two y coordinates. Yeah, that's not good either. All right. So 50 over 25 plus x squared minus 1 is the length of that rectangle, and the width, thickness of it is delta x. And so like before, when we sum the rectangles, we're summing these area formulas, and then in the limit, that's going to turn into the integral of 50 over 25 plus x squared minus 1 dx. The values of x run from here, which is minus 5, to here, positive 5. And that's pretty easy to tell from just solving where the two equations are equal to each other. So this integral runs from minus 5 to 5, and that was one of the multiple choice answers. And those multiple choice answers really are nowhere close to each other. So, so that part I think is pretty straightforward. The tricky part is now what? How do you evaluate this integral? In theory, all we know how to do is substitution problems. And so it must be that, but let's see how we would do it. So I'm going to get rid of, well, let me just get rid of as much of this as I can. There we go. Might as well get rid of that too. And in fact, I might as well get rid of this. We know that we're trying to integrate from minus 5 to 5, 50 over 25 plus x squared. Now I know that's not exactly the integral. There's also a minus 1 in there, but obviously this is the part that requires the most work. So let's just leave this by itself as a simple, to keep it as simple looking as possible. And let's not forget this is not the final answer. The final answer would be whatever the integral of this minus 1 is. So we have to adjust it when we get done. Okay, so how do we do this? Well, the main thing is that this denominator is the sum of two squares. And so the integral that we know that's the closest to that is this one. So we know that antiderivative of 1 over u squared, or sorry, 1 over 1 plus u squared is arctangent of u. So we know that, and so what we want is our substitution to turn the original integral into an integral that has this square root of 1 plus u squared in it. There are two ways to do that, but if I really stick to traditional substitution, this is what I would do. I would first use algebra to rewrite my problem so that it's 1 plus a perfect square, so it matches 1 plus a perfect square. To do that, I have to do something that's a little counterintuitive, which is to factor 25 out of this. I know it doesn't look like there's a 25 in there, but we can make that happen. But if I can factor 25 out of this, then this will be 1 plus something. So let me just, I'm going to do that by itself over here. If I have 25 plus x squared, I can factor out a 25, leaving 1 plus, but the penalty is that the fraction, the other expression becomes a fraction. So algebraically, these are the same thing. 25 plus x squared is the same as 25 times the quantity 1 plus x squared over 25. The reason that that's valuable insight is that notice that x squared over 25 is a perfect square. It is x over 5 squared. So this is entirely algebra. This is just rewriting the denominator so that we can see something in it that looks like 1 plus a perfect square, and that is motivated by wanting to try to create something like this because that's one of the problems we know an integral formula for. And so that's actually all we need to get going here. So before doing any integration, I'm just doing algebra now. Before I do any integration, if I were to rewrite the denominator the way I just said, then we can see that we have something canceling here. This will leave us with a 2. Let me rewrite that just so that it's not cluttered. So this is the same integration problem, and now there is a tempting substitution to make, namely let u be x over 5. And you can see that the denominator in my integrand is going to turn into 1 plus u squared, which was my goal. If u is x over 5, that means that du dx is just 1/5, and so du is 1/5 of dx. So now, back to my original problem. Let me not put the limits of integration on there yet. I'll address those in a second. Man, that is one big eraser. That's better. So without worrying about the limits of integration yet, in order to have 1/5 dx sitting here, if I make this 1/5 dx, then I need to put a 5 elsewhere in the problem to counteract it. So if I put a 5 out front, that allows me to put a 1/5 inside. So I've added a 1/5 factor and a 5 factor, which means it's the same. But notice that this is just du. This is just u. And of course the 2 is just a constant, so I can bring that out as well, which gives me 10 times 1 over 1 plus u squared du. And that is exactly what my target was here. So I'll be able to use the arctangent as the antiderivative of 1 over 1 plus u squared. Let's fix the limits of integration while we're thinking about it. Remember that the limits here, these guys are in terms of x. The original problem is in terms of x, so these are x values. And I want my integral here to be in terms of u, so I need to replace them with u values. And of course, this tells me the connection. So when x is minus 5, u will be minus 1. And similarly, when x is 5, here on this integral, when x is 5 here, then u is equal to 1. And so I still have the 10 sitting there. I know that the antiderivative of 1 over 1 plus u squared is arctan of u, and that's being evaluated between minus 1 and 1. Now you may have to drag out a calculator, but don't forget if you do that it has to be in radians mode, because the arctangent of 1 is pi over 4, and the arctangent of minus 1 is minus pi over 4. So when you evaluate the arctangent between minus 1 and 1, you get pi over 4 minus negative pi over 4, which is pi over 2 times 10 is 5 pi. So that's the answer to the integration problem I've written here. The actual integration problem, remember, was going from minus 5 to 5 of this thing that we just did, minus 1. And so that's going to be the integral of this thing that we just did minus the integral of 1. So that's why I could just go ahead and do the problem, because just a little bit. Yes. The going ahead and doing the problem doesn't hurt anything, because I know the answer to this part is 5 pi. We just did that. And the answer to integrating 1 from minus 5 to 5 is 10. You can do it using familiar calculus, or you could draw a picture and see that it's a rectangle. It's a 10 by 1 rectangle. So this will be my final answer.